In this particular video, we'll solve some important questions from artificial intelligence module from GATE DA syllabus. So let us start this particular video. So I think this is the question only, Shivam. Okay, so please see. So how the base net is defined. So there are variables are there. We want to represent the joint probability distribution. Here the joint probability distribution is given in the question. Now it is asking that which of the option is correctly representing this joint probability distribution, or from which base net I can represent this joint probability distribution. Okay. So I have a three variables here. If I create a base net which is fully connected, okay, there are everywhere paths. Okay. Will it represent all the joint probability distribution? Do I need to worry? Okay, so what is the joint probability distribution? I am supposed to obtain this particular value. Probability of A, B, and C. This is the joint probability, right? Or A given B complement and C. So you can get this using the multiplication formula. Probability of A given B complement and C, and probability of B complement given C multiplied by probability of C. Now you can create a base net on this. Let's say how you will create a base net. See, C is the root variable. So C you will create a root variable. Then you will have a B complement. So from there is a from C there is a arrow to B. And from C and B both there is a arrow to A. So this is my base net. I can create. So any joint probability, if I have a fully connected network, I can represent it. Right? If I give you some other base net, then what will happen? Let's say I just change the direction of arrow. Then you just change the particular event that you are conditioning in this particular multiplication formula and you will still get the answer. Let's say I consider this particular way. So how you will decompose the joint probability in this scenario? So what is the, okay, again the C is the root node. So instead of C, let me just make the A as the root node. So so A is the root node. So probability of A should come at last. Okay. Now C is actually conditioned on A. C should be conditioned on A. So it should be something like this. This is also valid decomposition formula or valid multiplication formula. Okay. There is nothing wrong with this. So if you have a full network, you can represent any joint probability distribution. That's what I'm actually motivating you to indicate. CNA, if you condition on CNA, you will get to B complement because from CNA, the arrows are coming to B. So everybody is clear that if I have all the arrows, then you can actually represent any joint probability distribution. There is no problem in that. Okay. Now, in this particular question, it is asking there is specific distribution is given. We have till now we have not considered the specific distribution, but some specific distribution is given in the question, and it is asking which possible base net I can represent it. Okay, so okay, so let's say I consider a first base net. What is its requirement? What is its requirement? Independence assumption of the base net. What are the independence assumption of the base net that is given in it? B and C are independent with each other, right? Please see the independence assumption implied by the first base net is B and C are independent with each other, right? So go to the table and check whether B and C are independent with each other. If they are, then you can also represent this joint probability distribution with the base net that is been given in the option A. So you can just check that B and C are independent. What is the how to check the B and C are independent? Consider the joint probability, whether just see that it is the same as multiplication of the marginal probability. You'll just find out it is not same. Okay. So B and C are not independent in this particular probability distribution. More specifically, you can just calculate the probability of B and C together. Let's say for one term, let me just calculate it. So probability of B and C. B and C both are 1. Let's say you consider both are 1, that is 0.25. What is probability of B? B is happening, so B is 1. So 0.25 and again 0.25. So probability of B is 0.5. Probability of C again you can just consider. Probability of C is 0.1, 0.20, 0.35, 0.45, and this 0.25. I think so. I assume it's 0.7. So probability B and C. This is not actually correct. That's why B and C are not independent. The independence requirement is joint probability should be multiplication of the marginal probability. So B and C are not independent. So I can't actually decompose the joint probability distribution table. And I can actually consider the probability of B separately, B, C separately, and A given BC. Understood? So is it clear that Y is not correct? Because for A, I need that B and C are independent. If B and C are not independent, I can't represent any joint probability distribution with A. If B and C are not independent, I can't represent the joint probability distribution with A. Any doubt? So A is incorrect. Why it is incorrect? At least that thing is clear. Okay. Now consider the B. What are the independence assumption? A and C are independent, and there is no other independence assumption needed. So A and C are independent. You go by this particular same way. You consider a probability of A. So you consider this you actually check these three things. Probability of A and C is same as probability of A and probability of C. C will also be 0.5. You can just check that C is not 0.5. For 1, it is 0.1. Here 1, it is 0.25. That is 0.35. That is 0.45. And 0.25, that is 0.7. So C is 0.7. You see that probability of A and C complement should be also same as probability of A and probability of C complement. Probability of A complement and C, that should also be same as probability of A complement and probability of C, and probability of A complement and C complement should be same as probability of A complement and C complement. If all the four conditions are satisfied, then only you can say that A and C are independent. You go to this table, check that whether all the four conditions are getting satisfied using this particular all the four conditions are getting satisfied. If that is satisfied, then only you can say that A and C is independent, and you can just check that yes, it is independent. So B is the right answer. Okay, so I'll just take a Nikhil's doubt. C will also be point, but why we are seeing ABC, sir? Okay, just check. Why we are seeing ABC means I did not understand. Why don't just C tables where it's one? Sorry, can you unmute and let me know, Nikhil? I did not understand your question. So by then I'll take the Shivan's question. When there is an arrow from one node to another, it should be dependent. So what should be dependent? Please be fully precise. In C1, C1 comes 4 times. So 4 by 8, isn't it the see, Nikhil, this is not the actually samples. Okay, this is the corresponding probability distribution given. So for this particular joint event, the corresponding probability is 0.5, 0.15. So that is the rightmost column. So this is the joint probability distribution table is given. These are not the samples. Okay. So that's, I think you are assuming that, you are creating some samples. So you are dividing it. So individual event will have a same. See, these are not samples. We see this joint probability distribution is given. How to get a joint probability distribution? For all possible combinations of ABC, you give me the probability. That's what the joint probability distribution is, right? So it will satisfy all the rules. You just sum the probability, that will be 1. You sum the conditional probability, all the rules, it will get satisfied. This is the joint probability distribution is given. Okay. So I think you assume that those are samples, so that's why creating mistake. So Shivam is asking when there is an arrow from one. So what should be dependent? Can you please tell me, Shivam?
Hello, sir, can you hear me?
Yeah, yeah.
Yeah, in option D, sir, we are seeing an arrow from A to C, so it should be dependent, right? A and C.
It need not be dependent.
Like
See,
why, sir? Why like that? When there is an arrow, it should be dependent in base network.
no, it is just saying that Bayes network is more capable of modeling this probability distribution. Even if the distribution is independent, it will still model it.
Okay.
I feel there is a difference between conditional independent and independent. That is something.
So that is different. Both things are different. But what you are
So
implying?
here I feel it is talking about conditional independence and not
No,
independence
no,
in
no, no,
general.
no. No, 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 no. Every independence. See, you. What I'm saying is, let's say I give you some other base net. Okay, let me just ask you. Just so let me just ask you some other base net. This is my base net. A, B, and C. What are the independence assumption as getting required for this particular base net? Is this in the option? I guess no, this is not in option. Okay, so you consider this particular base net. What are the assumptions or independence assumption or conditional independence assumption for this base net?
A is independent.
B and C are conditionally
No,
independent of A.
B is
That is the required assumption.
independent of C given A.
Yes. Okay. So if I know the event A, occurrence or non-occurrence of event A, B and C are independent. That's what it is implying. So
no, B
please,
and B
yeah,
and C are dependent. Na arrows are towards B and C, so B and C should be.
given A, both are independent. If I know the event A, I don't have extra information that whether B and C jointly occur, don't occur. So B and C are acting as if they are independent if I know the event A. Okay, so you don't, so please go through or revise the independence and conditional independence assumption also of the base net. It is very essential. Okay. We'll come to that. Okay.
I have
But
studied the place where I have studied from. It was said that the arrow is towards something that is not that is dependent, and here A is independent. It was said like this.
that is fine. But which dependent and which not dependent? Which two nodes you are considering? A or C or B or C? Or B, AC, BC or AC? Which node you are considering?
Oh, I have got it. Got it. It is
Yeah,
about it is dependent on the nodes. Which nodes we are talking about? Like
obviously.
B
Yeah.
and C, it is different. B and A is okay.
Yeah, yeah. So what I'm saying is if you know A, if you know the event or occurrence or non-occurrence of event A, B and C are independent. That's what I'm saying. So this is a definitely assumption is needed because what you will do is you will specify some table of distribution of A. You will specify a conditional distribution of B given A. So it will have a 4 entries. You will also specify a conditional distribution of C given A. It will have a 4 entries. So you will not specify anything in this base net. So if B and C are not conditionally independent with A, then I can't model that particular probability distribution with this base net. Right? Because in my particular decomposition, certain term will come, right? So if you remember this, my decomposition, how I can represent a joint probability distribution, B complement given CA, and CB. Now, what I am saying is there is A, okay, that is a root node. And if I condition on it, B and C are independent. So if you know that B and C are independent given A, then can you simplify this equation? Given A, B, and C are independent, so you can just remove this part. Hopefully, you from the probability theory, you should know this. Now, all the entries are there in the table. This entry is there in the table. B complement given A, go to this table. B complement given A, you will get from this table. Then C given A, is that present in the table? Yes, definitely. I have a table for this as well. Probability of A, yes, I have a table for this as well. So all the combinations of the joint probability I can get from this particular base net if I have this particular property of the given joint probability distribution that given A, B and C are independent. If they are not independent, then I can't simplify this B complement given A and C, and that's why I need a table which is giving me the probability conditional probability distribution of B given A and C both. So still any doubt?
Sir, one doubt, sir.
Yeah.
Can you go back to the diagram you were showing of the basenet?
Okay.
If here, from B, if we draw one more node, D, say,
Okay.
and then can we say that D is conditionally independent of A given B?
Yes. So if you remember the D separation principle, you can say that. So if you know the B, then definitely it will be independent of.
So it does not change despite B actually being dependent on A. From the diagram, we understand that B is
You
dependent.
know the B, okay. Now
Correct,
you
we
know
know.
the B, your distribution itself is changing.
Oh, correct. Yeah,
You
we
know
know
the
the B.
certain
So,
event. Yeah,
yes.
you know the certain event. Now you are considering different distribution, which is a conditional distribution now.
Okay,
Okay.
yes, sir. Thanks.
This is not always true. You have got to some point which I feel every student is missing. If you know this B, now tell me A and D are independent given B. The revert
A and B are given D.
given B, A and D are independent.
Given B and D are independent, correct?
No, they are not independent
Acha, no, they are, sorry, yes,
because two arrows are there and they are coming
no,
here.
correct.
So please revise the concept of d-separation. So there are various cases and you need to consider the direction of arrow as well. Don't just see that there is one node that has been conditioned. That's why they become independent. So they are not independent. Okay. So if you don't condition on B, then A and D are independent.
Yes.
Yes. Very good. If you condition on it, it will not become independent. So these things you should know. D-separation principles. Okay. So in this question, there is some option that is getting repeated. B is coming 2 times. So D is also correct. Is there any doubt here? Why D is correct?
Sir, I did not get when A and C are connected, it should be dependent, right? Why it is not? Why you're telling it is independent when A and C are connected?
So I am saying that it need not be dependent. See, independent is a stronger condition. Okay. So so let's say you have this base net where there is no arrow. What are the independence assumption needed for probability distribution to get followed? All are independent with each other without conditioning.
Yes.
So if A, B, C all are independent, then I can represent that joint probability distribution with this base net. These are base net, right? Valid base net.
Yes, yes.
Okay. Now the same base net or the same probability distribution. Don't change the probability distribution. Same probability distribution, if I consider these arrows, let's say I create some arrows. Can I represent that joint probability distribution by this network? Same probability
Yes,
distribution.
yes. Okay, okay, yes.
Okay. So if you have more arrows, it's good actually. That means your whatever the see, you can think of it in this way. You have more arrows. That means you need your conditional whatever the distribution. See, your base net is not an individual entity. You are also specifying some distribution table associated with each node, right? So if you have a more arrow, the size of the distribution table will only grow. So actually, joint probability distribution is like 2 to the n minus 1, 2 to the n minus 1, right? So now let's say you remove some arrow because you have some independence assumption. So size get decreased. You add some more arrow. Then oh, it's fine. I have a more size table. I'll still represent that, right? What is the issue?
Okay, okay, sir. Understood. Thank you.
Yeah, welcome. So I'll take one question which is coming from Shreyas. This is a Bayesian network given. So you need to calculate the probability up till 3 decimal places. So you need to calculate this particular quantity. How to calculate it? So Bitupan is saying that write it as a sum of joint probability. Yes, you calculate. So see how you will calculate it. This is my conditional probability. First apply the conditional probability formula as I have told you. Probability of negative A given D and D. Yes, very good. So let's actually find it. Probability of negative A, D and D. Okay. So how to do it? First write the conditional probability formula. Okay. Probability of D and E. Can you calculate both the things from the Bayesian network, numerator and denominator? negation A, D, and E. Can you calculate this quantity?
Yes, sir.
How?
I have calculated this
How?
and
How?
was getting
How you have calculated?
negation of
A,
A.
D, and E. These are joint events.
Yes, sir. Sir, let me check the solution.
This is your base network.
Uh, yes, sir. For P negation A DE,
Okay.
P negation A multiply by
No,
P C given negation AB
see, first of all,
into.
a simplest thing I will tell you. Which
Okay.
nodes are root in this base network? A, B, those are root, right? No incoming arrows are there. So you can actually consider that you have for them is what you have is the corresponding marginal probability distribution. So you decompose this joint probability where probability of A complement is there. Okay. Because you have a table where probability of A will be there. This probability of A complement table will be there. A and A complement both you will have, right? Now for C, do you have something? So there is no C in the question that is being asked. So first of all, you need to write it in terms of C, right? C has to come into the picture because there is D and there is no. So ideally, you can write this in terms of A, C, D, E. So, okay, the B is also not there. So, B is needed, I guess. Yeah, so B is also needed, I guess. So, whatever B2 is saying, sum of joint probability and then use the independence rule. Yeah, I think you should use the A, B, C, D, E. All such probabilities, you can just write it. And you sum it for all possible values of B in E. Okay, is this clear at least? If I sum it for all possible values of B and E, B and C, B and C, B,
Yes.
negation of B and C. So, but this is nothing but as a law of sum of this is you can consider it as a marginal probability, left hand side. This is a joint probability. So marginal is sum of joint probability. You can think of it in that way. Now, can you calculate each of the term from the base net? So C has to be conditioned on A and B. D has to be conditioned on C. E has to be conditioned on C. That's how it is, how the base net is progressing. N, A, and B are hanging. So, first of all, you will start with this particular thing that I'm only writing for this term, okay? You can write other term by your method. So, I'm only writing for this term, how you can calculate it. First of all, D and E are hanging. So, you calculate for one, D. Now, I condition on all other events. C, B, A complement and E. So, C, B, A complement and E. I'm conditioning on all of them. Multiplied by joint probability of C, B, A complement and E again. But can I write this joint probability again using the multiplication formula? Yes, again you can use the multiplication formula and you can write it in this particular manner that see, this is my D and E. So D and E should come last. That's what it is. So you do this particular E given C, B, A complement, right? Now what you will do? E given CBA complement. Again, this is my joint probability CBA complement. Now, can you decompose this joint probability again using the multiplication formula? Yes. Which the node should come? Where there is an incoming arrow. C should come now as a event that you are considering. So let's consider a C now. C given B and A complement. Okay. And again, can you this then the multiplication term is B and A complement, and this you can simplify using again a multiplication rule. So at least is this clear that how I have come up with this formula? I have just applied the multiplication rule from the probability. So you have 5 event, 4 event, doesn't matter. You can apply the multiplication rule as it is. I am not using basenet as now, but the way I have conditioned the event is as per the basenet. Why? Because it is easy to do. See, this particular term D given C, B, A complement and E. So if you go to the basenet, conditioned on C, D is independent of with E, D is independent with A, D is independent with B. So if I condition on C, everything D is independent with everything else. So this term is now getting simplified with only I have to condition with C only. This is a conditional independence, conditional independence property. You should know this. So I can just consider this term. And where I will get this term, you have this table, right? D given C table you will have for this particular node. This is a D given C table you will have. So you can just get the entry from this. Obviously, it is given D given C is a 0.9. Okay. So you can just utilize it. Can you simplify this term? E given C, B, A complement. Again, the same thing. Conditioned on C, it is independent with everything else. So you can just eliminate A and B in this particular scenario, and E given C is there. And again, you have some other table where E given C is also present. You have a different table as well where E given C is also present. So E given C you can just get from this particular table 0.7. Now third term, C given B and A complement. Can you simplify it? So C given B and A complement, you can't simplify it because C is not independent with A or B. So, but you have that table, right? You have this table. This is a conditional distribution of a variable C, condition on the A and B complement or negation of A and B complement. All such values you have from this table. Okay, you have all such values here. You can just take that value. You are just given this value. And B given A complement, can you just simplify it? Yes, B and A are independent without conditioning. So B given A complement is nothing but probability of B. You have all the entries from the table. You just replace it, you will get one term. Likewise, how many terms are there? 4 terms are there. You calculate all the 4 terms, you will get your numerator. This is my term. Similarly, you will get a denominator. So any doubt?
Sir, I have solved this, but I was getting the value in 0 point up to 3 decimal 0. So that's why I confused
Okay, so you can just send your
for
answer.
that denominator term.
Okay, so you can just send your answer to me. I'll just check it and verify. But the process is clear, right?
Yes, the process is clear.
Okay, so just
I
send it.
think
So I don't have a calculator right now, but you can, when you send it, I'll just verify it.
okay, sir.
So
And sir, one
yeah.
question I am having that like last year the question has come of BaseNet. Like we can easily solve the probability with the given tree. Okay, sir. So in this, it is possible to do that or not? Like I didn't apply the conditional probability formula. I just simply solved by the given tree.
So if it might be simple also, it need not be complicated, but I don't know. Okay. This is the standard way of approaching it. If you know the way, then you don't have to worry whether it is complex, simple, you don't have to worry. But it is
Yes, sir.
important
Like
that you know the process.
okay, sir. Like here I didn't get it. By I have tried to solve by that method, but didn't get it.
But now you understood, right?
Yes, and
Okay.
Sir, I just want to ask that I have understand the Bayesian concept you have taught, you have told in last question also, but
Okay.
I am getting confusion in this thing that which is conditionally dependent on this and which is not. This I am getting confusion. Can you please elaborate with in that example also, last example which you have just taken?
So the image that you have sent, should I consider that image? Okay, so
I
let me
have
consider that
I have not
image.
sent. I have not. Rishabh have sent, I guess, one image.
Yeah, Rishabh has sent. So let me consider that image. Then grade is there, set score is there, and then the last term is letter is there. Okay, and this is my structure. Okay, so how to calculate independence, conditional independence, everything. So just round those nodes which are getting conditioned. So for a first case, let's say you are conditioning grade. Okay, so there is something called as a D separation. Everybody should know that, or everybody should read it at least, go through the lecture. So what does the D separation indicates is remove all the arrows or don't consider the arrow. and consider the two nodes that you are being asked. In this particular first option, it is being asked difficulty and the letter. So that is my A option. These two nodes are being asked. Now you find out all possible path between these two. There is only one path. Don't consider the arrow. Without considering the arrow, you consider all possible paths between these two. Okay. And whether you see that every path is cut off. Now, how to define a cutoff is, there are four rules basically. If you have some line, so okay, this is my conditioned event, and this is my line. So this indicates that if this particular node, middle node, is conditioned, then this path is cut off. Okay, this is my case one. Similarly, I have a case two, that now you consider the arrow. First, when you have you have found all possible paths, at that time you did not consider the arrow. Now you are considering the arrow. Okay, so let's see, this is also the case. It can happen that it can the arrows are left arrows as well. So here also you can say that it is cut off. If it is not conditioned, then it is not cut off. But if this node is conditioned, then the path is cut off. Okay. Similarly, there is also case three. Case three is both nodes are outwards of the conditional node. Then also you can say that it is cut off. That is also fine. Both this entire path is cut off. But case 4 is also there, which is slightly tricky, which says that if you have two incoming arrow in my path, okay, and if I condition on this variable, then this path is not cut off. But if I don't condition on this variable, then it is cut off. So it will be too much to digest it if you are completely clueless about BaseNet and the independence assumption. But you need to know these properties. There is also case 5. If the node that is here and that is not been conditioned, I don't know this event, then this is not cut off. Sorry, then this is cut off. But if it is conditioned, then it is not cut off. Ulta hai yahan pe. This is my case 5. So this is called as a D-separation principle. Everybody should know that. It is, this is something that will be used to estimate which variables are independent condition on some other variable or those kind of things. So please go and read about this particular topic. Okay, so do you want to elaborate anything more? I can't explain it entirely why this is coming, because I have to take certain example, because it will be too much. But I'll just guide you that you should cover this topic actually, if you have not covered. Okay. Anybody wants to ask their doubt, which is too much, which is bothering them too much? Okay, Nikhil as a C1 is 4 times. So okay, that is some old question, I guess. Okay, so there is no major questions that you have, hopefully. The process is clear. Everything is, you need to furnish it, your concept, bit more, and then you can come up with it. Okay. Also, please guys, go and read about beam search as well. I have asked it in the examination. So how beam search is progressing is, it is similar to the breadth first search. So you are starting with certain start node. Now you have a certain open list, as somebody was saying. Those are the nodes that you can consider. In the breadth first search, you are considering the all nodes. But here you are only considering two based nodes. How based? You consider whichever, minimum map value, whatever the parameter you have, you consider two based nodes. So you are considering two based node, this node, let's say, and you two node. Now you only keep these two nodes in my list. Just consider remove other nodes as well. Now you see all the nodes of these two nodes, adjacent nodes of these two nodes. Now from all these nodes, you consider two based. So at every stage, you are only considering two nodes. So this is called as a beam search with the size 2 or parameter 2. Or if it is 5, then you consider 5 base node. At max 5 base node you have to consider. If there are less than 5 nodes, you can't consider, don't create a node, but you can consider that many. At max 5 nodes you can consider. So this is also part of the uninformed search algorithms. So let's say these are the 2 base nodes. So you only consider the neighbors of these 2 nodes only. So only neighbors of 2 nodes will be there in the open list. Okay. Okay, so in the question it was given size was 2, you can also consider size is 5, whichever size it's given, you have to consider it in that particular way. Consider this question. You are given 2 different statements. B is independent of E given evidence at C. B is independent of A given evidence at E. Okay, I'll just zoom it. Okay, so how to do it? B is independent of E given C. So whatever the condition variable, create some pink color line. Now B is independent of E. So how to do it? Consider the d-separation principle. Consider all possible paths between B and E. So one is actually this particular path. This is one path. The other is this path. Don't consider the arrow first. Now this both path has to be cut off for that it to be independent. Now let's say this is my first part I'm considering. Is it cut off? So yeah. So it is cut off, right? It becomes non-active because C is condition. But there is some different path as well, which is this path. Now you see that it is cut off or not. So these are 2 incoming arrows of the conditional variable. And I have told you by the case 4 that if I am conditioning certain variable and 2 arrows are incoming, then the path is not cut off. So this path is not cut off. So that's why B and E are not independent. Right? Similarly, there is a second statement is also given. Conditioned on something, evidence at E. So now you are conditioning on E. Just remove this C part. You are conditioning on E. Then A and B are independent. That's what it is given. B is independent of A. Okay. So how to do it? You are conditioning with E. Then you consider all possible paths between A and B. You are conditioning with E and you are considering all possible paths with A and B. So this is my one path. This is my second path. Hopefully you understood which are 2 paths. One is ACB and other is ADECB. Now tell me ACB is cut off. I'm not conditioning on C. So ACB is cut off. ACB is cut off. Fine. But is second path ADECB, is it cut off? Again the same scenario. Condition variable, 2 incoming arrows. Not cut off. So again A and B are not independent. So both statements are incorrect and B is the correct answer. Any doubt? Even if one path is not, then we say that it is, you don't say it is dependent, you say that they need not be independent. That's all. So hopefully this is clear. Okay, answer this question. You have a game tree, which is very deep. Okay. And you are doing some Minimax algorithm. Okay. And assume that your Minimax algorithm is searching to entire depth, whichever the depth that you have. Complete depth Minimax value you are given. And you are acting with respect to V alpha. V infinity, you can just say that. That is your strategy. Strategy means given this particular move, what is your move? Given the opponents this move, what is your move? Similarly, pi infinity is the Minimax policy. Okay. And minimax value is V infinity. So whatever the final value that you are root node is getting is V infinity. Now consider a depth limited version of this search. Depth limited means you don't search the entire Minimax tree. Now, everybody should know the Minimax algorithm, how it works. There is a root, a max node, there is a min node, there is max node, min node alternatively. Right? Now, what is the, so let's say it has a very large depth. Then it is impossible to actually calculate an appropriate strategy or optimal strategy. So what might happen is you do the limited version of the search, let's say till 10. But if you do the limited version of the search, how you will actually propagate up the utility values? Because utilities are at a leaf. If you remember the adversarial search process, leaves as a utility, and once you actually reach the leaf, a certain utility of a certain node actually gets finalized. Otherwise, it doesn't get finalized at all. Now, in the question, it is saying that you are doing some version of a depth limited search. So you will not even get to the utility. So in this particular kind of scenario, this is a standard case. So even if you have a depth of 200, then it is becoming infeasible to actually search for the AI agent. So in that particular scenario, you can do the limitation. You search for 10 next nodes, and the utility, you don't have actual utility, right? Because you have not searched till end. At the end only you will get to the utility. But you will have some approximation of the utility at 10th node that is being also said as a heuristic value or whichever value you say that. And that particular value you actually propagate up. So you only search till depth 10, and you actually calculate the approximate or optimal strategy according to that. And then you AI agent will work on it. Now, when it comes to next stage, it will search for next 10 level, then again next 10 level and next 10 level. So let's say you are playing chess. It has a many depth game, 200, 250 depth game. 250 plays are there. So it will not search entirely. It will search till 10. And whatever the state it is seeing of the chessboard, it will replace the utility with the approximate heuristic value. How many queens you have, how many bishops you have, and those kind of things. It will replace the approximate utility of the every state at after 10 iteration. And according to that, it will just calculate the utilities and do the minimax search process, and then it will proceed. This is how the boards are working in the chess game. So in the question, it is given that let's say you do the 10, depth limit is 10, and V10 is the current root. That means the utility that you are propagating. Pi 10 is the strategy of the minimax search. Then which of the following is statement true? V alpha may be greater than V10. Yes, it can possible, because whatever the utility you are actually propagating up after a depth limited search of the depth 10, they need not represent the actual utility. They are some approximation. So it can happen. V alpha is more. It can also happen. V10 is also more. We don't know. So A and B are both correct. Against a perfect opponent. Perfect opponent means he's superhuman. He knows everything. Even if the AI agent doesn't search entire depth tree, but this particular opponent is actually searching entire depth tree and actually, moving according to the best possible decision. So the best case is you search entirely, but due to the feasibility constraint, you are actually limiting to the depth 10. So against the perfect opponent, it is better you employ the pi alpha strategy, where you are actually searching the entire tree and not the depth limited version of the tree. So C is incorrect, that against the perfect opponent, actual outcome of the following pi 10 will not be greater than V alpha. So that is if you apply pi 10 means search strategy of the depth limited version of the 10, then it will not be greater than V alpha. V alpha is the best possible value you can get by the perfect opponent. V alpha is the minimax value of the entire tree without any depth limited search. So if the opponent itself is a perfect, you can't get more than that. That's how the minimax search algorithm is being defined. Right? Now against the perfect opponent, D is saying against the perfect opponent, actual outcome of the following pi 10 may be less than V alpha. This assumes that perfect opponent is playing the infinite look ahead. So yes, actual outcome of the following pi 10 will be less or equal to V alpha in perfect opponent, definitely. So if you play the pi 10, that means the search strategy according to the depth limited search that you have employed, that will be definitely worse for the perfect opponent if you are not doing the total search. So D is correct. So any doubt why ABD is correct? This is correct question, right? Shivam, that you're referring. So Fn, so Fn is Gn plus alpha times Hn. That is the Fn value that you are considering. Now, how the search algorithm proceed? There is something called as a closed list. There is something called as an open list. It will consider the node from the open list which has a minimum F value. This is how it will proceed. Now, F value could be anything. Okay. It will pick up the node and include it into the closed list. So this is my closed list. This is my open list. Okay. It will pick up the node from the open list and include in the closed list, which has a minimum F value. This is how the A star is also progressing. Now, A star is a very generic case. Okay. You can also consider this is how the BFS is also progressing. Why? Because in BFS, you just consider HN need to be 0. Gn is the particular path length. So obviously the next node that will be considered will be the minimum node amount. See, this is the same way uniform cost search is also progressing. This is the generic way. Okay. Now you can actually assign the weights of Fn and G. So everybody knows what is Gn and Hn for a given node. So let me create a tree. I'm starting from this start state and I'm reaching certain state. Let's say this state. S. So Gn is the length of the path till this. This is my Gn. Hn is this heuristic value, and Fn is in this particular question it is given. Generally in A star, Fn is Gn plus Hn, but in this question it is given that alpha times Hn. Okay. This is how it is. So you pick up a node for the next expansion from the open list where Fn is minimum. That's how you proceed. Okay. So in this particular question, it is asking, let's just go through this question. There is some weight is being given. In Fn, you are not giving equal weight to Gn and Hn. You are giving some different weights. So this kind of questions might also come because what might happen? So if you have seen some dry run, okay, so I will not go into the details why such a kind of heuristics are being considered. You can go to the, but this is very much possible. This is called as a weighted A star algorithm, where there is a weight of is also given to the heuristic function. Okay. Now Hn is admissible. So everybody knows admissible heuristic. The estimate cost from that node to goal is always lesser than the actual cost from that node to goal. If this is satisfied for every state, then it is admissible. Furthermore, one more thing that has been mentioned is, so obviously this particular algorithm process is being mentioned. I'm choosing one node to unexpanded list or an open list. You consider both same, unexpanded or open list with a minimum F. Here Fn is defined as Gn plus alpha times Hn. Okay. Then with respect to optimal path. Okay. So one more thing you should know, that this is a tree search. Okay, why it is a tree search is for optimality guarantee in the tree search case, you only require H to be admissible. But if you have a graph, then you need H to be admissible and consistent both. So there is one counter example I particularly want to point out if you don't know that. If you are searching in a tree where there could be duplicate states as well, then you only need an admissible heuristic. And if you consider Fn equal to Gn plus Hn, not alpha times Hn, then you will get the optimal path. But if you have a graph search, then you have to have a admissibility plus consistency, both, to obtain the optimal path. If you consider Fn to be Gn plus Hn. Okay, you go to the whatever reference material that you are considering and just enhance this particular concept. Be clear about this concept. I'm not going into that detail, but I have this chance to mention this, so that's why I'm mentioning here. Okay, now here the Fn is being considered Gn plus alpha times Hn. So what it is saying? So let's consider a case where alpha is less than 1. First of all, this is my case. So let's say alpha is 0. Let's say it is 0 less than 1. So obviously considering a negative value of alpha will not make much sense. So let's say alpha is 0. Then this particular search is called as what? If alpha is 0, then this is what search? I'm considering GN. Every time I'm considering the node which is having a minimum length. So this is what search? Uniform cost search. Yes, very good. So this is a uniform cost search if alpha is 0. So if alpha is 0, then I will have an optimal path. Or whatever the path that has been found by my algorithm will be optimal, because uniform cost search will give me the optimal path. That is something we know. Now let's say alpha is non-zero and it is less or equal to 1. It can be 1 also. It is less or equal to 1. Then also I am arguing, then it will, if H is admissible, then whatever the final path that has been outputted by my algorithm will be optimal path. Okay. So I will argue it with some process which is called as a proof by contradiction. So let me create some other path, which is this path. Let's say this is my optimal path. Okay. But my algorithm did not explore this path. And my algorithm go on and on exploring this path. And at some point of time, it has explored, G as well. That is some goal state. Let's say G1. And here there is G2 is also present. That is another goal state is present. Okay. So let's say my algorithm is working some different way. It is coming to some other path and it has not explored G2, but my algorithm has explored only the partial states, only these partial states. Let's say till now it has explored some node A, and here it has not explored the next node B. B is not explored, but till A everything is explored. Okay. So I will just indicate with the different color so it will be clear in my proof. So what I am saying is, when algorithm has explored S, or let me just give some other name, S is a starting node. So when the algorithm has explored this node C, and then it is choosing G1, at that particular moment, the situation is algorithm has explored A through this path, but it has not explored B. Why? Because for some reason, why? What is the reason? F value for G1 is obviously less than F value of B. In only that condition, my algorithm will choose G1. Okay. Now, what is the F value of G1? What is the F value of G1? Mostly, H value of every goal node will be 0. So, what is the F value of G1? F value of G1 will be the path that you have found, the length of the path that you have found, that was outputted by your algorithm, right? That is not optimal path. I'm assuming the contradiction. Let's say you have reached G1. Let's say your algorithm has actually explored G1. That is, as this particular blue path it has explored, and this path it is outputting as a certain path reaching from start to goal, but it is not optimal. I'm assuming a contradiction, and I will just prove to you that such a thing cannot happen. So this is something called as a proof by contradiction. Okay. So this is blue path. So the F value of G1 is a blue length. That's what I can say. It's just a blue path length which is not optimal by our assumption. And this is not optimal. Okay. Now, my algorithm has actually explored A. Till A I have explored. So this particular partial length, so this particular yellow plus, so this is yellow plus blue, let's say. This is my yellow plus blue. Okay. Now my algorithm has, for what will be the G value of A? G value of A will be yellow plus green, right? G value of A is yellow plus green, definitely. And what will be the F value of B? F value of B is at most. What could be the F value of B? So the particular heuristic, what I have defined the admissible heuristic is, from here, the remaining path length is obviously higher than the H value. So HB is obviously less than the red length, right? HB is obviously less than the red length. Now, if you consider this yellow plus this green, so yellow plus green is G value of B. So G value of B, let me just calculate, see that this is G value of B is just a yellow plus green. Okay. Now yellow plus green is the G value. I am considering this is also green. This is also green. This is my G. H value of B is less than red. That is something by the property of admissibility. So H value of B is less than red. Now yellow plus green plus red is what? Is actually optimal path by my assumption. Right? Yellow plus green plus red is a less than optimal path. So that means GB plus HB is less than equal to my optimal path to G1, G2. Right? So I am saying that F value of B is less or equal to optimal path. But I have selected some G1 at that particular moment, which is not optimal path. So this says that my algorithm is not choosing the node as per the minimum F value, right? I have chosen G1 before B. That's why I am not reaching to optimal path. And here F value of B is less than optimal path. Obviously yellow plus blue path is not optimal path. And that is larger than optimal path. That's why F value of G1 is obviously larger than F value of B. So this is something we will get by our assumption. Okay. So such a thing is happening. That means what? This is actually the contradiction. It will be strictly larger. Let's say this is not an optimal path. That means this has to be strictly larger. So this is yellow plus blue has to be strictly larger than yellow plus green plus red. So if it is strictly larger, then definitely you have some contradiction. So if my algorithm is choosing the node in such a way that F value is Gn plus Hn, then I will reach the optimal path. That is something I have proved. But let's say it is choosing a F value in some other way, which is Gn plus alpha times Hn. So if I replace with alpha here, which is less than 1, then still I can argue that F value of B will be still less than F value of G1 because H value of G1 will be definitely 0. So if alpha is less than 1, as long as alpha is less than 1, I can still argue that my algorithm will still find the optimal path. Alpha is 0 means uniform cost search. Alpha is 1 is A star graph search. And if I have an admissible heuristic, I will find the optimal path. If alpha is 0.5, still I will find the optimal path if H is admissible. Here I have used the concept of admissibility. Please know that HB less or equal to red line, that itself says that the heuristic value of B is less or equal to red line. So as long as alpha is less than 1, I'm okay. I still find the optimal path, less or equal to 1. But let's say if it is some, let's say 1000 or some other value, alpha is some other value, then can you argue the same thing? Then you can have some approximation bound. Let's say here alpha is not less than 1. So here alpha is less than, so first of all, FB is not less or equal to optimal path. If let's say alpha is greater than 1, strictly greater than 1. Okay. In that case, you can say that FB is not equal to, or FB is definitely, you can just consider it. So alpha is not, is greater than 1. So FB is not equal to, or FB is not less or equal to optimal path. That is something you can argue. H is still admissible. Right? But why? Because see, you are considering these two terms, Gn plus alpha times Hn. Gn plus Hn is less or equal to optimal path. But Gn plus alpha times Hn is less or equal to optimal path. No, right? So you can just consider that this is less or equal to alpha, because Gn plus Hn, you can just consider, decompose this in this way, Gn plus Hn multiplied by alpha minus 1 times Hn. Right? Now this term that I have indicated using the orange color is nothing but a less or equal to optimal path. Right? So what you can say about this term? Hn is admissible. So Hn is admissible means HB, what you can say about HB? HB will be always less or equal to yellow plus green plus red, right? Optimal path length. So HB is always less or equal to optimal path length because B is coming in the way of optimal path from S to G2. So this particular quantity, you can bound it with less or equal to alpha minus 1 times optimal path. So the final discussion says that the corresponding F value of B will be less or equal to alpha times optimal path. So FB will be less or equal to alpha times optimal path. If I am considering FB equal to Gn plus alpha times Hn. Is this clear? Here, obviously, I know that B is coming in the way. B is in the way of optimal path from S to G2. S to G2. Okay. So is there any doubt in this? FB will be less or equal to alpha times optimal path. So if it is less or equal to alpha times optimal path, what you can argue about some path that has been found by the by your algorithm? So if your algorithm is finding some path which is more than alpha times optimal path, then by again the contradiction, because you have some path which is actually blue, this particular yellow plus blue path, which is more than alpha times optimal path. So when you are actually expanding G1, you are considering that G value of G1, basically G value of G1 is actually, you consider the contradiction that G value of G1 is greater than, or let's say strictly greater than alpha times optimal path value, that is nothing but yellow plus blue, yellow plus green plus red. If such a thing happens, then I will not explore G1 first. I will explore actually B first. So there is again a contradiction. So my argument is, if Fn you are considering is Gn plus alpha times Hn, then whatever the optimal path that you will get will be at most alpha times optimal path. Any doubt? So Gn should always have a more priority than Hn for optimal path. Yes, correct. That is the thing. If you want to find the optimal path. Okay, so why such a thing are actually useful is, I will just show you. There is some nice simulation that Professor Mosam has shown. You can just go through that particular lecture as well. So let's say this is your start state. This is my goal state. Now A star algorithm is progressing some like this. Let's say you have some decent heuristic. Okay, so it will just explore like this. It will just explore these nodes. It will just explore this node. It will just explore this node. But when it is actually reaching, it will actually search an unnecessary path, because at that particular node, Fn plus Gn will be very high. So it will just find some unnecessary path. And at some point, it will just consider the exploring this path and find the optimality. So if you have a very large search state or search space, you might explore some unnecessary path, because when it is reaching here, when your algorithm is reaching here, when your closed list is reaching here, the corresponding F value is very high if you consider the F to be equal to Fn, Gn plus Hn only. Why? Because Gn is very large for these particular nodes, and Hn may be small, but Gn is very large. So it might happen that it might actually explore some unnecessary nodes at some different direction before reaching G. So what you can do is just give more priority to H. You might compromise on optimality, but if you give more priority to H, it might happen that there are some nodes where there is a more priority to H. So it will actually the corresponding F value will become higher for some nodes. So I might I might eliminate exploring some of the nodes in this particular direction, and I will reach to my goal faster. So that is actually the motivation of using such a kind of loss function. So not loss function, but such a kind of F function, so that I can actually search a go, because I'm giving more priority to heuristic. If I give only priority to heuristic, then what happens? Best first search. Okay. Here I'm giving more priority to heuristic. So base first search has a problem that it can go to infinite loop. But if I consider GN, then it will not go to the infinite loop. But I am giving more priority to HN because I don't want to search to multiple paths. I might compromise on optimality some, but that's fine to me. So if you consider Fn equal to Gn plus alpha times Hn, then whatever path that you are getting is at most alpha times optimal path. So any doubt in this? Okay, it's clear. Thank you. Consider this question. So you are considering Fn to be 2 plus x times Gn plus x squared times Hn. So Gn is a cost of state of n where you are starting from S to that particular node, and Hn is admissible. This is admissible estimate of a cost from that node to goal. Okay. So how many integer values are there such that Fn is always giving you the optimal path? So you remember our discussion that Fn is Gn plus alpha times Hn. As long as alpha is less or equal to 1, it will give me optimal path. So it need not happen that the coefficient corresponding to Gn is always 1. It might happen that 2. So you just consider a 2 same multiplication to Hn also. So see, everybody should know that considering this as a Fn or considering 2 times Gn plus alpha times Hn or 3 times Gn plus alpha times Hn or 100 times Gn plus alpha times Hn, everything is equivalent because you are just scaling it. Okay. So ultimately, how the search algorithm is progressing, you are choosing some node which is having minimum f value. Now you are considering different f, but you are actually multiplying the f with the scalar for every node. So what does it matter? Okay. So you need to know this particular thing. Okay. Now consider this particular case. So as long as alpha less or equal to 1, you will have an optimal path. Okay. So let's say, this is 2 plus x Gn x square Hn. So let's try to replace different possible values of x. So if x is equal to 0, then what do you have as a f? So if x is equal to 0, then you will have a 2 times Gn multiplied by, Hn. Sorry, Hn will be 0, so there is nothing. So 2 times Gn. So will it give me optimal path? It will give me optimal path, right? Because this is nothing but a uniform cost search. So for x equal to 0, it will give me the optimal path. For x is equal to 1, what is now f is becoming what? 3 times Gn plus Hn. So is this if you might get confused, this is same as this is equivalent. Okay, there is nothing difference. You either consider this or you consider 1 over 3 times Hn. Both are same function. Okay, you just scale by any factor, doesn't matter. So this is also equivalent. So here you just see the coefficient corresponding to Hn is less or equal to 1. So definitely x is equal to 1 also will give me the Fn, which will give me the final path as a optimal path. Let me consider x is equal to 2. So for x is equal to 2, my Fn becomes 4 times Gn plus 4 times Hn. This is 4 times Gn plus 4 times Hn. This is equivalent of Gn plus Hn. That is nothing but a star algorithm. You know that for a tree version, A star gives the optimal solution. It has to be tree search. Please see that this tree search will be. Then only it will give the optimal. Otherwise, you need a consistency as well if it is graph search. Okay. Okay. So which other thing is remaining? Minus 1. So let's consider x is equal to minus 1. You consider x is equal to minus 1, Fn becomes Gn plus, it's the same thing basically. This is the A star search algorithm only. So these again give me the admissible heuristic. So you consider any other value. Okay, which other values are there? Minus 2 also you can try considering. That will not give you the optimal solution because Gn gets eliminated. Minus 3 and all, it will not give me the optimal solution. You can consider 3 as well, but the coefficient corresponding to Hn gets increased. So for 3 also it will not give optimal. So for what are the possible values of x for which it will give me the optimal? 0, plus 1, minus 1 and 2. Right. So any doubt in this question? Okay. Thank you all for joining. Hopefully everything is good. If you have doubt, feel free to ping me. You can also call me. We'll clear your doubt. It is important that we clear your doubt. Hopefully your preparation is going well. Let me just close the lecture.